welcome back viewers. I am Diman and today I will be presenting the numerical problem from the last lecture. If you are not aware, let me just give a recap. In the last lecture I have explained the detailed design process of shaft design in 5 steps, and this video is a part of previous lecture. In this video I will be explaining the detailed numerical problem on shaft design. So if you haven't watched that previous video, I am giving links in description and I button. Please don't forget to watch that video. So let's quickly start. Let me just explain the problem statement that we will be solving today. And design a shaft to transmit 20 kilowatt at 750 rpm, and span is 600 mm, and pulley load is 790 Newton, and pulley weight is 50 Newton. This is exercise problem statement. Now prepare a shaft layout and given data, and the given data is as follows. Power is 20 kilowatt, speed is 750 rpm, span is 600 mm, and pulley load due to belt tension is 790 Newton in vertical direction, and pulley weight is 50 Newton in vertical direction, and total weight is in vertical direction is 790 plus 50 equals 840 newtons, and material selected is SI 1040 steel. I will quickly explain why I have selected this particular material. And material properties are yield strength is 450 MPa, and ultimate strength is 620 MPa, and factor of safety I have taken 3, and this is I have taken from the regular practice in design course. And allowable bending stress will be sigma yield divided by factor of safety, and 415 divided by 3 we will get 138 MPa, and allowable shear stress will be tau yield equals to 0.577, that's yield stress divided by factor of safety, and after calculation we will get around 80 MPa, and allowable fatigue stress is 662 MPa taken from the design data book. And failure theory used will be maximum shear stress theory, which is also called Tresca's theory. I will also explain in briefly why I have selected this failure theory. So first let me just quickly explain the free body diagram. Here 840 Newton is the vertical load, and two reactions after story we will get 420 Newton each since the problem is symmetric, that's why the reaction will be coming equal, and torque transmitted is 254.77 Newton millimeter, and span is 600 millimeter, and the torque formula is very popular formula. As a mechanical engineer you are aware, P into 60 divided by 2 pi n, and if we do the calculations by putting the given data values we will get 254.77 Newton meter. One tip I will have to give you, that while solving the problems keep a strict eye on the unit system for the problem. Here I am writing the torque value in Newton meter, and in the later case I will also require in some other unit also. Just quickly go to the material selection. Why I have selected AISI 1040 steel is because it is having good strength, and from a machinability point of view is also good for this material, and this is a widely used shaft material in the industry. That's why I have selected this material. And failure theory I have selected the Tresca's theory. It is because the main function of the shaft is to transmit the torque, and torque produces shear stress. That implies that the shaft should not fail in shear, and also shaft materials are ductile, and also Tresca's theory produce a conservative results, and this is the reason why I have selected this Tresca's failure theory. Now quickly moving to the stress calculations. This is a bit boring part, so I will just quickly go through these calculations. And moment formula M is WL by 4, simply supported beam, you are also aware of that, hope you know this formula. And after calculation M will be 840 into 0.6 divided by 4, coming out to be 126 Newton meter. Remember the units. And torque formula calculated earlier, 254.7 Newton meter. And now apply the Tresca's theory for calculation of P torque in the Tresca's formula. I will be using equivalent torque because the loads are combined loads, means bending load and shear loads are simultaneously present. That's why we will have to use the equivalent torque. And for calculating the equivalent torque, PE is given by square root of m square plus t square. And after putting the values in the equation, 126 square plus 254.7 square of the square root will give me 284 of Newton meter. And if we solve for D, this will be 16 TE divided by pi tau allowable to the power 1 upon 3. Well, the formula for tau shear stress is 16 T upon pi d cube. And if you solve for D, you will get this formula: D equals 16 into TE upon pi into tau allowable to the power 1 upon 3. I have written in short just to show you the calculation. And if we put the values, and 16 into 284 into 1000, again now I am converting the units to Newton millimeter, and divided by pi into 80 MPa is the tau allowable. It is in MPa and to the power of 1 upon 3. And after doing the calculation, we will get 26.25 millimeter. If we round it off to a standard size, we will have to go for the higher side, which is 30 mm, because if you go in the market, the shafts are not readily available for each and every size. You will have to adapt to the sizes available in the market. So as per the market standard, we will have to choose the 30 mm dia shaft. Now just quickly go to the deflection check, and I am using again simply supported beam formula for deflection is delta equals FL cube divided by 48 EI. Here quickly explaining, F is the vertical load, L is the length of the beam, and 48 into E. E is the Young's modulus, which is 210 gigapascal. I is the moment, area moment above the neutral axis, and its formula is I equals pi d to the power 4 divided by 64. And after solving, pi into d just calculated 30 to the power 4 divided by 64 equals 39,740.624 millimeter to the power 4. I will again emphasize on the units, so be very vigilant while solving the engineering problems. Be very vigilant with the units. And now, because in the units conversion system, maximum people make mistakes, so you will have to be extra vigilant while solving engineering problems. Or after calculating the delta, we will get 0.425, and this is under limits. So because if the deflection value goes around 1 mm, then it's a problem, and it is coming within 1 mm. Now critical speed, and critical speed formula, as you may be knowing, or just explain if you don't know. NC, critical speed, equals 60 upon 2 pi into square root of g by delta. It is taken using the same simply supported beam theory, and calculating 60 upon 2 pi into square root of 9.81 by delta in. Now again you will have to keep in mind the units here. I have converted this 0.4 values to the meter value. For that I will have to shift decimal to 3 places, that will be 0.004, and the calculation will give me 1495.57 rpm. So this will be the critical speed. Now if we compare it to our operating speed, it is 750, almost half of critical speed. That means the design is safe against the critical speed. Now we will check design against fatigue loading. For fatigue loading, I am using popular failure theory, Goodman. Why I have selected Goodman? Because it matches the experiment data very well, but can underestimate failure. Simultaneously, it is less over designed than Soderbergh criteria, which is often seen as excessively cautious, means it is over engineered. And Goodman criteria formula is 1 upon n equals sigma a dash divided by se plus sigma m dash divided by sut. Quickly explaining, n is the factor of safety, se is the endurance strength, and sigma a dash is the alternating stress, and sigma m dash is the mean stress, and sut is the ultimate tensile strength. Now again collecting the given data to solve the Goodman equation. Ultimate strength value is taken 620 MPa, endurance limit is 0.5 the ultimate stress, which is 0.5 into 620, 310 MPa, and factor of safety is 3, and earlier calculated 126 Newton meter. Torque value 382.16, diameters 30 mm. Now if we solve for equivalent stress will be coming out to be sigma a equals 32 m upon pi d cube. Since this is alternating, because the bending loads are changing in direction with every rotation, that's why it is considered as alternating stress, and sigma m mean stress, which is created from the torque value, it is constant in direction, that's why it is taken as mean stress. And if we put the values, we will get sigma a equals 32 times m, which is 26 divided by pi into 30 to the power cube, and equals it will coming out 47.558 MPa. And sigma m mean stress 16 into square root of 3 into 382.16 divided by 3.14 into 30 to the power cube equals calculation 124.92 MPa. Now here, as you can see in the right hand side, this is a graph shown in blue color. You can see the Goodman failure line, and it is a plot between the mean stress and the alternating stress value. Peak alternating stress value is the endurance limit, and peak mean stress value is the yield strength and ultimate strength, and this in green color is the safe reason. And for our case, it is Goodman failure theory, and if we put the our values in the left hand side, we will get 1 upon FOS 1 upon 3.33, and in right hand side putting the sigma a 47.558 calculated in the previous slide divided by endurance limit, which is 310 MPa, plus mean stress 124.92 divided by 620, and if sum up 0.15 plus 0.2 will give me 0.35. Since the LHS left hand side value, which is 0.33, and the right hand side value 0.35 is almost equal, that means the point lies on the blue line, that means it's in the safe region, so the design is safe against the fatigue loading. Now summarizing the results, key outcome from the analysis are: shaft diameter selected is 30 mm, and deflection values is 0.42 millimeters, critical speed 1495.57, lesser than the operating speed, and factor of safety chosen is 3, and this approach guarantees efficient shaft design. If you follow this approach, you will be getting definitely a safer design. Hope you like this video, and if you liked it, then please don't forget to subscribe, and I'll see you in the next video. Till then, bye.